Okay, I'm now going to move to the latter part of the talk. We're going to talk about some very unusual, atypical volcanoes. So I'm going to talk about the volcanoes that are responsible for diamonds. Back in history, diamonds were only known in the alluvial form until the 19th century. So most of our diamonds would come from India. So the crown jewels diamonds, a lot of those are coming from the subcontinent. And it was only in the sort of 19th century that it was recognised that South Africa had good potential. And so this is from the Orange River, where they've got alluvial diamonds. But it became pretty clear, and this was discovered by the British who found the Kimberlite deposit in South Africa, that the diamonds were actually sitting on a rock, a very unusual rock they called blue ground. And it turns out, of course, it's kimberlite, which is a very unusual volcanic rock. And we know they sent the original sample to the Natural History Museum, we have it, with a diamond sitting on this kimberlite rock, because people didn't believe that it was a new type of volcanic rock. People thought these are all in sediments. But anyway, this is proof, and this was some recent drilling done in Canada where a diamond was found in a piece of drill core, and you could see it visually. So very, very rare, but we know that they come from this very specific type of volcanic rock. Very busy diagram, but all it remains to say is that we know that these diamond-bearing kimberlites are only found in places where the crust is really old, it's really cold, and it's really thick. And there's a reason for that, and I'm going to come on to that. So we find diamonds in South Africa, West Africa, parts of Russia, parts of South America and northern Canada. And they're in these areas we call cratons, which date right back to the Archean, so they're more than 2.7 billion years old. And there is a reason for that. And this is a geophysical image of Africa, and you can see this is what they call seismic tomography, and it's telling us where the crust is very thick and very cold, and that's shown in white. So this is the deepest, thickest, oldest parts of crust on the Earth. And there was, back in the 1960s, it was recognised that you only got diamonds in kimberlites that had come through these oldest parts of the Earth's crust. So it was an empirical relationship that was noticed in the 1960s. And Clifford's rule fitted very nicely to the Capvel craton. And why is that? Well, what we find is that now we can analyse inside the little inclusions that are found in diamonds, and we reveal that diamonds actually can form up to 800 kilometres down in the Earth's mantle. So diamonds, as we know, are a form of pure carbon, and they're only stable at very high pressures. So they only form deep in the Earth's mantle, and they're only stable at depths below 150 kilometres. So that means, in order for them to be stable, there has to be conditions where we've got very thick crust and thick cold mantle that will preserve those diamonds at depth. And so this is just a diagram to show you that they more or less the golden the golden window for finding diamonds is between about 100 and 200 kilometres. And that's telling us that that's where they form and that's where they're stable. And these kimberlite magmas, so these kimberlite volcanoes, are erupting from deeper than that. And the studies of these kimberlites show us, you only need to go and buy a stamp in Lesotho, actually, to find out, get the geology. It's a beautiful stamp. And it shows you that what we have definitely a volcano, but it takes the form of what we call a diatreme. So it's a round structure, and inside there we only have volcanoclastic rock. We don't have any flows, because this type of eruption is extremely dynamic. It's full of gas, and actually it breaks up long before it gets to the surface. It's an incredibly erosive process, and it rips up at supersonic speed through the crust from deep, deep down. It's coming from maybe 200 kilometres down. And you imagine the pressure it's under down there, 200 kilometres. And it basically funnels its way all the way through the crust. And actually, by the time it's coming up, it doesn't really notice what it's coming through. And it forms these round structures that are these the so-called kimberlite pipes. And this is some work that, if Steve Sparks had been giving the talk, he could tell you more about this because it's his paper. But effectively, there's some kind of explosive eruption that's coming up at hundreds of meters a second. So that's pretty fast. Then the whole thing becomes under pressure and everything falls back in. So it's almost like it's a big explosion, a rupture, and then you get a fallback into the crater. And then it's like fluidized, so you're getting vapor coming up from the bottom, and all the rocks are getting churned around and abraded. And it must be a spectacular volcano when it erupts. Now, the youngest kimberlite we know is about 100,000 years old. So that's within human memory. So in Tanzania, there would have been people living there. So I have no idea what they would have thought when one of these erupted. As far as we know, they haven't stopped erupting. They could happen again. But would we get warning? I don't think so. So very, very unusual type of eruption. But we get diamonds associated with them. And that's a kimberlite there with the diamond actually on the matrix. And so people understand more about these, but they don't only come on their own. They often come in clusters. And so these vapors are coming up from very, very deep source and are erupting. And this is the Ekati mine in northern Canada, and there's at least 4 different pipes occurring together here. And it's only been discovered. It's very difficult to explore in this part of Canada. No rocks exposed, but modern geophysical techniques were able to detect these. And so here's Ekati. There's 4 of these pipes. They're like carrots. And they've got different fascia, so it's mostly pyroclastic. So that means it's all brecciated and it's coming up as part of a pyroclastic flow. And we don't have, deep down we've got coherent kimberlite, which is shown in red. So that's really where it's still a melt, and we get a coherent deposit. But in these northern Canadian deposits, we find evidence of a tree, actually carbonized tree fragments. So these things were erupting up into forests, and we're getting fallback of trees into the kimberlite pipe.